Okay, we've done a lot of work with the cars and the tracks. So today I want to put some things together and give you an example of what you can do with the information that you've been taught. Because many of you think you can't do the homework you have, but you'll be surprised at what you can do with what you have learned. And at the end of this video, we will synthesize a group of formulas that can be used to help you predict the answers to motion problems. So this all applies to a specific kind of situation, a situation in which the acceleration is constant. That's what we've been watching so far. Our velocity versus time graphs are linear, which means the rate at which the velocity is changing is constant. So our slopes have all been something that represents the acceleration when we look at a velocity versus time graph. So I want you to consider a simple situation. All right, let's imagine a car accelerates from 10 meters per second to 30 meters per second in 6 seconds. And let's assume the car does that in a straight line, so one-dimensional motion. Now, I didn't say where the car started or where the car ended, so let's make two assumptions before we even start that the car started this acceleration at the origin. So at a position of 0, that's when the timer started. Okay, so if I was to graph this, let's make the right one our velocity versus time graph. So velocity on the vertical axis and time on the horizontal axis. I'm going to mark 6 seconds and 2, 3, so 10, 20, 30. Car starts here. And a smooth line connects to 2 because we were talking about situations of constant acceleration. Now, if I wanted to kind of sketch out what our position graph looks like, I can use the information in the velocity graph to do so. Again, position in meters and time in seconds. These two graphs have to agree with each other, which means they have to represent the same events. And therefore, this is also a 6-second example. So I'm going to mark 6 seconds on the time axis. I did say from the beginning that the car is going to start at the origin. And it looks like at time 0, the velocity is 10, which means at time 0 on the position graph, our object is moving with a positive slope positive velocity, which means a positive slope right there. I don't have a scope for how big to make this slope, except I know that at the start, the velocity is 10 meters per second, and it's going to become bigger, so I know that I have to have a shallower slope here to leave space and room for a steeper slope here. I don't really know where to put this dot because I don't have a range over here because I don't know how far the car's gone or how far it's traveled. And that's okay though. We're just making a sketch. So again, a smooth curve to connect the two. I don't really like that curve, so I like that one better. So that's our smooth curve to connect the two. Now, you have two pieces of information that we've talked about all week. And I know that some of you are struggling with these two pieces. But piece number 1 is the slope of the velocity versus time graph is acceleration. Now, we can get the slope. You guys are familiar with how to do so. You're well trained. So we'll use rise over run and point out that we rise from 10 to 30. That's a change of 20 meters per second. And we do so in 6 seconds. So if I want the acceleration is going to be 30 minus 10 over 6 minus 0, or 30 meters per second in 6 seconds. So just a little bit of math here tells me that it is 5 meters per second. That's our acceleration. And it is positive, so it is away from the detector or forwards. Now, that gives me the slope. That tells me a feature of what's happening here. But you know something else. you know that the area of the velocity versus time graph is displacement. So if I want to find out what the displacement of the vehicle is, I can do so by finding the area. Now, we've looked at a couple of these graphs, and our areas have been simple shapes like triangles most of the time. This is also a simple shape, but it's not a triangle. It's trapezoid. And just so you remember, a trapezoid is two parallel lines with two non-parallel lines. That's trapezoid. So I have two parallel lines and two non-parallel lines. Now, I guess the other ones don't have to be non-parallel, but they don't have to be parallel for it to be a trapezoid. Now, this happens to be a right regular trapezoid. So I can use the area of the trapezoid, 1/2 base 1 plus base 2 times height, as a way of determining the displacement. This is going to be base 1, this is going to be base 2, and because it's a right regular trapezoid, this is the height. So 1/2, base 1 is 10 meters per second, base 2 is 30 meters per second, and our height is 6 seconds. So 10 plus 30 is 40, half of 40 is 20, 20 times 6 is 120, and this is meters per second in here times seconds there, so this would be 120 meters. This is the displacement, and just a reminder, displacement is change in position. So x minus x naught, change in position, final position minus initial position. In fact, we could write this as delta x if we'd like, 120 meters. So 120 meters. That tells me something. If I go back over here, I now have more information for this graph. I know this point has to be at 120 meters because the car only went forwards. So when I look at the motion of this car, its displacement is how far it traveled this time. Now, if the car went forwards and then backwards, the displacement would still be the change in position. It wouldn't be how far the car has traveled. It would be where the car finished. But this car only went forwards. Now, that's a lot to unpack, but that's only 6 minutes. So what I would really like to do is I would like to take this, what we've just done, and maybe change it a little bit. And here's what I mean by that. What if I didn't give you any numbers? So instead, I say a car accelerates from some initial velocity to some final velocity in some number of seconds. Symbols. I think this would still be okay. This is definitely assuming that the car travels forwards because my slope for my velocity versus time graph is positive, so all the velocities are positive. But we're trying to create a generic sense of how we can maybe solve these questions without having to draw a graph every time, right? We're going to try and model the behavior of an object's motion. So stay with me for a minute. This would be v naught for the initial velocity. This would be v, some final velocity. And our time would just be t. This over here, delta x. Or better yet, we could write this as x here and x naught there. Now, we can do the exact same analysis that we did just a minute ago. The slope of the velocity versus time graph is acceleration. So acceleration equals the slope. Well, that would be the change in y over the change in x, or the change in the vertical divided by the change in the horizontal. So v minus v naught, that's the change in the vertical, divided by t minus 0, assuming our interval started at 0. Okay? Same thing. We did the same thing, just no numbers this time. Now our area is going to be the same. Our area is the displacement, x minus x naught. to my vector things there. That's going to equal 1/2 times base 1. This is base 1. So base 1 is V naught plus base 2. Well, this is base 2. That's just V. And our height, well, that's the time. Now, you may be wondering, well, why would I want to do this? Well, hear me out. Let's simplify this. I'm going to multiply both sides by t, and I'll get AT equals V minus V naught. I'm going to solve this for V. When I do that, I'm just going to add this to both sides, and I will get V equals AT. First, I want to point out that we knew this already because this fits the mold of y equals mx plus v. It's a linear function. This establishes something we started out at the beginning saying that this only works if the velocity graph is linear. So we knew that had to be true. We have graphed velocity on the y-axis. We have graphed time on the x-axis. We would get this linear function because our graph is indeed linear. But we also have something like this. Displacement equals 1/2 V naught plus V times t. So imagine a new problem. Okay, here's our new problem. A car accelerates from 2 meters per second to 10 meters per second with an acceleration of 0.5 meters per second squared. So I've established a set of conditions. Now if we look, based on what's been reported, the car accelerated from 2 meters per second, V naught, to 10 meters per second, V, with an acceleration of 0.5 meters per second squared, A. I've given 3 pieces of motion data. Judging by what I have, it looks like I could use this to figure out the time, right? It's one unknown. And once I know the time, I could use this to figure out the displacement. Watch. I'm going to start with finding the time. V, 10, equals A, 0.5 times t, plus V naught, which is 2. Subtract 2 from both sides, 8 equals 0.5t. Divide both sides by 0.5, and t equals 16 seconds. All right, we know how long it took for the car to accelerate, 16 seconds. So x minus x naught equals 1/2 times V naught, which is 2, V, which is 10, times t, which is, we now know, 16. All right, we'll do the work. So, half of 16 is 8. 10 plus 2 is 12. 8 times 12 is 96 meters. So, judging from this, I was able to figure out all sorts of stuff about the car without ever drawing a graph. Now, one of the things I want you to notice, and this might be harder for all of you, and again, we're just starting, but these motion problems seem to have the same kinds of things associated with them. There's displacement, which from this point forward I'll put as delta x. There's initial velocity. There's final velocity. There's acceleration, and there's time. 5 motion variables. And it looks like we have, just from looking at motion graphs, 2 relationships that we could use to figure out the missing information. So if I can provide you with any three of these, you could probably provide me with the other two. Now, sometimes it's a lot of work, like you just saw. We had to solve this one for t first, and then use that to figure out displacement. So maybe there might be multiple steps, or maybe there might be a shortcut. Now, if you're still listening, I'm going to show you the shortcut, because 5 motion variables. If you look closely, this motion equation has everything except for one of the motion variables in it. In fact, I said I was going to write this only as delta x, so I'm going to write this as delta x. This equation is missing delta x, just like this equation is missing the acceleration. Well, I know algebra. I know that at any time, I could take any two relationships, and if they have a common variable, I can do some algebra to maybe change them and create a new relationship by eliminating the common variable. So for example, we're going to eliminate a common variable between these two relationships. I'm going to eliminate, I'll just pick one. I'm going to eliminate t between these two relationships, just like we did a minute ago. But we did it with numbers. I'm going to eliminate it with symbols. So I have to pick one of these to solve for t and plug it into the other. That is just a little bit of algebra. So I'm going to solve this one for t. And excuse me if I'm going to leave the vector bars off for a minute. So all I did was subtract v naught from both sides and divide both sides by a. So I've solved that for t. And now I'm going to use to it as a delta. So delta x equals 1/2 v naught plus v. Instead of putting t here, I'm going to put that in for t. Now, I don't know how good your algebra is, and I'm not going to spend a lot of time explaining algebra, but I will say this can be rewritten as 1/2a times v squared minus v naught squared. In fact, I would actually write this as 2a delta x equals v squared minus v naught squared. Now, what did I do? Not much. A little bit of algebra, but what I created was a new motion relationship that has everything in it except for, in this case, time. So, consider that we are building a set of motion relationships that can be used to solve motion problems, and in each case, they have 4 of the motion variables in them and 1 that's missing. So, think, if you're really shrewd, you probably realize we could probably generate another 1 or 2 of these, each one missing 1 of the motion variables. And I am going to do this one more time, and the reason is because I want you to see one more thing. So I'm going to eliminate final velocity between these two. I'm going to take everything that's here, and I'm going to plug it in for final velocity right there. When I do that, I'll get delta x equals 1/2 v naught plus at plus v naught. Now, I'm going to simplify by expanding this out. The first thing I will point out is I can write everything in parentheses as at plus 2 v naught, because there's 2 of them. Now I'm going to go ahead and distribute the t from this side. You get 1/2 at squared plus 2 v naught t. And lastly, I'm going to distribute the 1/2 from this side and get 1/2 at squared plus v naught times t. Now, you might be wondering why I thought we should look at that one. Well, let's first put that this has everything in it except for final velocity. And it's delta x equals 1/2 at squared plus v naught times t. Now remember, This is x minus x naught. Now, pay attention here. Let's go back over here all the way to where all this came from. We've talked about the fact that this is a curved graph, and before, at the very beginning, I said, you guys jump to, well, what curve is that? Well, you always say exponential, which I don't know why, but we have plotted position, x, and t. So position is on the vertical axis, and time is on the horizontal axis. The function we just created, if we solve it for position, doesn't this fit the function for a parabola? It's right there, isn't it? If we plot position on the y-axis and t on the horizontal axis, it's clearly parabolic. So our position graphs have all been curved because they are parabola. They're a quadratic. Now, that's all we're going to do, because I know some of you are having difficulty with this. But if you'll notice, we have what's now known as Galileo's motion equations. We're missing one of them, and I'll leave that as an activity for you, because as you can see, we have 4 of the motion variables that are on this list, and there's probably at least one more equation where we eliminate the initial velocity, and that'll give us 5 of Galileo's motion equations. They can be used to solve any uniform accelerated motion problem. So all you've got to do maybe is solve this one for initial velocity, plug it in here, and you'll have the last one. Good luck with your homework. Do your best this weekend.